let me go through some things I should have mentioned last time, but I don't have time to. Let's look at a slope, a frictionless slope, and a block on it. All right, let's say it's just a slope. It can have friction, it can have no friction, but it's a slope with a angle theta over here. So in this case, when we are analyzing the things, we first figure out what are the forces acting on the system. Because we are looking at the block, so we are going to choose everything making out this block as our system. What are the external forces acting on the block? Normal force. Good job, Olivia. Normal force is the normal component of the force between two surfaces. We define it to be the normal component, so it's always normal to the surface. In this case, the surface is tilted, so it's not going out, but normal to the surface. Good. Any other force acting on this system? Something to do with your homework, Sean?
Gravity.
Good. So when we draw gravity, for some reason we will put it acting on the center of mass. The point that the force acts on doesn't remain there for now because we can move vectors all over the place when we are doing vector addition and subtraction. But when we talk about rotation, there's going to be a thing called torque, and the exact location that the force acts on an object is important for torque. So let's just have a good habit and draw the gravity acting on the center of mass, and the normal force acting on the surface that it is acting on. Okay? Any other force? It might be friction, depending on whether it is static or not. Good. So let's talk about friction if you're interested. For the present, right now, just these two forces is enough. Like if we want to talk about a frictionless surface, then there will be no friction. Now, because the block is on the slope, it can only move along the slope. So I know the acceleration of the block is either going down or going up. There's nothing pulling the block up, so I guess it's going down. Now, if we choose the coordinate system to be like this, as we always do, your acceleration will have two components. So your acceleration will have non-zero component both in the y and x direction. And you know that's going to be double the amount of work you need to do. Therefore, instead of doing this normal, regular, upright coordinate, we are going to use a tilted coordinate. We are going to place our x-axis like this along the slope, and the y-axis needs to be perpendicular to it. So, does the acceleration have x component or y component? X or y? X, good. And it will make your life easier because now you know your Newton's second law will just become one equation saying that the force in the y direction will give you 0 because it doesn't have acceleration in the y direction. Let's do y at the bottom. For the x direction, it's going to be just a, the magnitude of acceleration itself. These are the I equation, these are the j equation. X component of total force equals the x component of acceleration times mass, and y total force equals mass times y acceleration. Right now, the acceleration cannot have y components, so your life becomes easy if it's 0. 0 is good because it's easy. Now, what is the y component of normal force? Which direction is normal force pointing to? Is it pointing to x or y?
Y.
Good. So normal force only have y component, and it is at 0 in the x direction. Another 0. Good, very good. That's why we use this tilde coordinate. But when we look at gravity, it's going down. So it has components both in the x direction and y direction. But that's fine. If we choose the usual vertical horizontal coordinate, gravity will only go down, but then we need to break the component, we need to break normal force and acceleration into two components. If we choose this coordinate, we only need to break down normal force and acceleration, we only need to break down gravity. In this tilde coordinate, normal force and acceleration both have only both points toward just purely x or y direction. And we need to break down the gravity into two components. If we choose the regular one, we need to break down normal force into two components. Acceleration also needs to be break it down into two components. So 1 is smaller than 2. That's why we choose this one. Of course, the result will be the same no matter which coordinate you choose, but it's good to make your life easier. Okay? So the problem is that it's kind of not obvious how should we express these two components. We know it has something to do with trigonometry, and this is how we do it. Let's look at the slope. This slope has an angle theta, and gravity is going down. I draw it this long because then it's easier to see this is a right triangle. The exact length of gravity doesn't really matter because gravity is force. It has nothing to do with the distance, which is a length here. So as long as the relative length between these two forces is up to scale, then I'll be fine. Actually, let me make it longer. Okay, so when I break down this gravity, I need to break it down into a component along x direction and a component along y direction. Does that make sense? When you break down gravity, the two components need to be perpendicular to each other. That's how you break down a force into components, no matter which coordinate you are in. Okay? Now, if this is theta and this is 90 degrees, how big is this angle? How big is the sum of these three angles for a triangle?
180.
180, good. So 180, there's a 90, there's a theta. You know that one should be 90 degrees minus theta. Okay? All right. Now, if you look at this angle, this is again 90 degrees. The two dotted lines with gravity form a right triangle. If this is 90, this is 90 minus theta, then this must be theta. Because you see, a triangle having 90 and theta will have other one, 90 minus theta. Now you have 90 minus theta and 90 degrees. So this one must be theta because they are both triangles. The sum of their internal angle is always 180. So you know the combination of 90 theta and 90 minus theta will always appear in a right triangle if one of them is theta. Okay. Good. Now, where is this angle here? In here. This angle, 90 minus theta, is the angle between the x component and gravity. So here is 90 minus theta, and they are perpendicular here. So here is theta. Okay? So now we can express the angle here with the angle of the slope. We know it's correlated, and the way to find out exactly which one is theta is by drawing another small triangle and do a triangle as well. Okay? So now, we found that if the slope here is theta, then the angle between y component and gravity is also theta. So if this is theta, this is the hypotenuse. This is the adjacent side. What is the adjacent side over the hypotenuse? It's cosine. If you are still not familiar with trigonometry, this is how I learned it. Sine start with s. A strict way to write s is like this. So sine is the hypotenuse and the opposite side. Sine will be opposite over hypotenuse. And what you should learn here is that the opposite side is hypotenuse times sine theta. This is the thing that you need to be very familiar with in this class, because you are always going to take a force which is going to be the hypotenuse and break it down to the components, which is either adjacent side or opposite side. Cosine start with c. When you write c, you write like this. So it's about the hypotenuse